Okay, so welcome everyone to today's webinar on the Blueback Toolbox version 11, Accelerate and Enhance Your Petrel Experience. My name is Mark from Blueback. I'll be your host for this webinar. It's nice to see so many attendees here today, so thank you all for your participation. So to start with, just a quick word on how this webinar is going to work today. We're going to be using a GoToMeeting hosted presentation. You should see a panel like this, which you can minimize by clicking on the arrow and then click again to bring the panel back. You can display the GoToMeeting session as a full screen or window via the view menu. By default, everyone is muted, so please submit any questions you have in this dialogue, and we'll hopefully have some time to share some of the questions and answers at the end of the session. The webinar has been recorded, so you'll all be provided a link within 24 hours. So please feel free to distribute as you require. And finally, the recording will be posted on our website. So the agenda, I'm going to talk briefly on the toolbox concept and explain a little about the toolbox framework, how we can incorporate client-driven functionality. There's a quick slide on the support systems we provide at Blueback. Then we'll spend the majority of the session in the live demo looking with a focus on the new features in version 11 and a selection of other tools. The new highlights covered will include the frequency spectrum probe enhancements, seismic stacking, folded seismic stacking, attribute ranking, tartan gridding, and the new MPD well loader. Following the version 11 demo, I'll provide a quick overview of the new seismic reservoir characterization toolbox, or SRC toolbox. But there's a full webinar planned on this SRC toolbox for January 2012. I'll then run through the licensing and pricing, and finally, if we have time, I'll share some of the questions and answers that are coming with everyone. So the Blueback Toolbox is a set of functionality features not available in standard Petrel. It's designed to accelerate and enhance your Petrel experience and also maximize your Petrel investment. All the features are based on requests from Petrel users around the world, including our own consultancy team at SIS. The requests have been brought together by the software development team at Blueback using the Petrel development kit Ocean, and the development is coordinated with the Petrel team at Schlumberger. The toolkit allows us to rapidly develop Petrel plugin applications which provide the user a set of complementary tools within the familiarity of the Petrel user interface. So we now have 6 toolboxes in total: the geology and modelling, geophysics, reservoir engineering and project management, which are the core of this version 11 release. We have an inversion toolbox tied to our stochastic inversion plugin, ESI, and also the new seismic reservoir characterization toolbox I'll introduce at the end of the demo, which for the record is licensed separately to the classic toolbox suite. So the current release is version 11. We've decided to rename the toolboxes by version number. So this one is 11, the next one will be 12. This is to avoid any confusion with Petrel's version naming by year. So the response from the user community is very positive so far, and the toolbox is becoming an important tool for everyone using Petrel. So I'd just like to share with you a little more on how the toolbox has been designed for incorporating client-driven functionality. This new release in particular sees a lot of new and exciting tools that have been driven by our clients. So the toolbox framework has been designed and built in such a way that it allows us to rapidly develop tools, workflows and processes upon client's request. Examples include upscaled log QC for Dong Energy in Copenhagen. The frequency spectrum probe was a request from SIS. There's several new enhancements to this I'll show you shortly. Also new for version 11, we have the tartan gridding energy for Noble, seismic attribute ranking for OMB, and the folded seismic stacking for Wintershall. So if there are any features you would like to see in the toolboxes that don't exist in standard Petrel, any troublesome workarounds you currently employ, or academic concepts you would benefit from having incorporated into Petrel, then please get in touch on sales@bluebackreservoir.com. Okay, one last slide before we move into the demo on the support systems we have at Blueback. We have a dedicated support desk available via email on support@bluebackreservoir.com. We also have an online support portal which has product forums, tips and tricks, release notices and updates. So please, if you are already a user, get registered with us. We're here to help. Okay, so demo time. Let's take a closer look. Okay, so I'm going to demonstrate some new and existing functionality and show how the toolbox enhances existing Petrel workflows. So first thing, where to find it? It's here in the process tree under Blueback plugins, Blueback Toolbox. So you can see it's split by domain into groupings of tools. The geophysics toolbox has more than 40 small plugins filling functionality gaps, providing for faster and easier seismic interpretation. The geology toolbox aims on speeding up and improving the various geomodeling workflows. The reservoir engineering toolbox has the new water saturation process and tartan gridding processes, along with various other tools for the reservoir engineer. And the project management toolbox provides tools for helping keep projects organized and helps with some of the import-export issues in standard Petrel. So we're going to start with the geophysics toolbox and the advanced seismic analysis, and in particular the frequency spectrum probe and the enhancements that have been made in version 11. So the frequency spectrum probe allows you to investigate the seismic signal and its resolution, and is a powerful tool for seismic interpreters who need to better understand the seismic signal. This can be used to compare the frequency content in different seismic surveys or vintages. The tool also assists in delivering analytic wavelets for synthetic seismograms. So for the Toolbox 11 release, we've provided additional enhancements to this tool to provide improved functionality and analysis for the user. So the first thing that's been added is to add a frequency spectrum probe folder to help you better organize your probe objects. So with the folder active, I click to add in my probe area for investigation. The probe is added into the folder, and then right click and come to open frequency spectrum window. So we still have all of the existing functionality. You've been able to move the probe around and updating the plot window dynamically. We still have the sort of 2D FFT plot as the background colored image. We can also display as a 1D FFT plot from each trace in the background. Both of these can be overlaid with an average 1D FFT plot from the trace data within the probe, and then also individual trace FFT plots from the cursor position in the probe. This has had a small enhancement to add in the trace number to the spectrum window. So there's various new settings that have been attached to the probe object. So if we come into settings and look at the settings, so I can see the seismic data I'm sort of have the probe on. If we're locked to it, the inline crossline number, trace range, sample range, vertical range, and if we have a linked probe, which I'll explain later. There's also some overlay settings if we have a locked seismic cube. So also in the menu we have lock intersection position. So this is going to lock the probe into this position in space. So this means we can move through inlines and crosslines with the probe in exactly the same position and dynamically update the spectrum window. We can also lock to inline crossline number, so this will tie this particular probe to this particular inline or crossline. And the last option we have is to lock seismic. So if we lock the seismic, lock the probe to this particular cube and toggle the new cube. So you can see that we keep the same probe on the new survey, but with the seismic that the probe was locked to now overlaid on the second cube. We can still move this around and update the spectrum window. So another new enhancement is the ability to export the average 1D plot to a Petrel function window. So if I just choose to add in a few more probes, so you do this by toggling off the existing probe, which allows you to add in a new probe. I'll just add one more. And we can add them all to this window. Okay, so there you can see we have three 1D plots from these three probes, which all dynamically update as you move the probes around. So from here I can sort of make a multiple selection, right click and copy average trace spectrum to function window. And then if I toggle on a spectrum window, to flip these axes. Okay, so we've exported those three 1D average plots to a function window, and from there obviously I can take this on to Excel or anywhere else. So the final thing to show you from the new functions for this release is the ability to link to active probe. So this means you can link two probes together. They'll be in exactly the same position in space. They can be moved and resized in parallel on different surveys or vintages. So all of this new functionality here in the frequency spectrum probe has been added in after listening to feedback from clients over the last couple of toolbox releases. Okay, moving on. Another one from the geophysics toolbox is the new seismic stacking. So this is a new feature, as I mentioned, in the geophysics toolbox, and is popular functionality brought over from geoframe. The technique is also referred to as optical stacking. So in 3D datasets, seismic stacking or optical stacking is routinely used for suppressing random noise, enhancing subtle structural or stratigraphic details, or delineating the extent of fluid contacts. So we just need to provide a survey as input, choose to build a cube in inline or crossline or both, and then finally select the number of lines you want to stack in front of and behind the target line, which can also be configured to be asymmetric. So if I just show you some results from this. Okay, so here we can see there's been a lot of noise removed from the original cube when compared to the stacked volume on the right hand side. Many of the faulted tilted blocks are more clearly visible, especially when following the outlines to deeper areas, and the sub-horizontal overburden horizons give a clearer, more continuous response. Also new for version 11 is a slight variation on this, which is the folded seismic stacking, or otherwise known as common contour binning. So folded seismic stacking is used to detect subtle hydrocarbon-related seismic anomalies and to pinpoint gas-water, gas-oil and oil-water contacts. The tool has been developed in conjunction with Wintershall and PGNiG, and the process is also commonly known as common contour binning, as I mentioned. So all traces that penetrate a hydrocarbon reservoir at the same depth will in principle have the same hydrocarbon imprint or response. Okay, so if we stack all traces along the same contour line, we can expect the hydrocarbon effect to increase, while the stratigraphic variations and random noise will be cancelled out. So if I just come to my input for this job. Okay, so in the example here I have a dome structural trap as seen in this top reservoir surface, displayed with an associated oil-water contact. The idea is to use the contours running around this surface as the seismic sampling criteria. So we're going to sample the seismic along each contour, then concentrically, kind of in effect, closing the ribs of the hand fan around the dome of this structure into a 2D section at specified angle to see if any consistent horizontal effects can be identified. The process also generates average, minimum and maximum amplitude attributes for each contour. So if we come back to the dialog, so the input, I need to adding my cube, which is this cube we can see here. My top reservoir surface, you can constrain my polygon. The contour step, so 10 milliseconds, are the contours that we have displayed here. I need to provide a stacking range. I can limit my surface. I need to assign my output and assign a seismic line angle. So this is the line angle of the stacked 2D section. 0 degrees is an east-west line in this case. Also just need to define what outputs I need to build and where to write my interpretation to. So if I toggle off my input surface and come to the results. So here you can see I have two sets of results. I have a 2D line and a suite of 3D interpretation objects. So if we start by looking at the amplitude. So this is the seismic the amplitude values rather from this cube sampled along the contours from the top reservoir surface, as we can see. We then look at the average amplitude. So this is an average value calculated from all values along one contour and then reapplied along each contour. So we can start to see this anomaly coming in here associated with the intersection between the surface and the oil-water contact. Again, this can be seen in the maximum amplitude values as well. So the other output we have is a stacked 2D seismic line, which we can display in an interpretation window as well. So this is the 2D line here, also displayed in the interpretation window with the oil-water contact. Again, we can see this sort of small anomaly creeping in between the intersection of the surface and the oil-water contact. So I can use another tool from the toolbox in conjunction with this 2D section, which is the interpretation attribute annotation. So if I make the interpretation window active and click here to add interpretation attribute, what it's displaying is the maximum amplitude as sort of red along this 2D line. So again, we can sort of see this anomaly here in the maximum amplitude. Slide it up, it's kind of tying in with this intersection between and anomaly here. So this is a really nice example of how we can incorporate client-driven functionality in theory into Petrel using the toolbox framework. So next up, I'd like to show you the new attribute ranking tool. So its development has been driven by our client OMV in Austria. They came to us with an interesting paper in geophysics published by Hampton Russell. So it's called the use of multi-attribute transforms to predict log properties from seismic data. So the idea is to rank seismic attributes according to their ability to linearly approximate a well log. A stepwise linear regression is used to determine what set of seismic attributes volumes best match a given target well log. So this allows the use of seismic attribute and log data to predict 3D log properties. So in this section selection here displayed, I can see my original seismic frequency, sweetness phase, cosine phase, cube attributes. So we're going to use these in the attribute ranking tool to try and approximate log porosity and then create a porosity cube from the combinations of attribute regressions that best match the log porosity. So if I come into the toolbox and show you the dialog, so the first thing we need to do is select which log we want to estimate, select which wells we want to use as input. In theory, the more wells you give it, the better the approximation. We can choose to limit by surface. We then need to make a selection of which attributes or volumes we want to use, which have just been created using the native Petrel attribute generation tools. We then choose which functions we want to use. So for each input volume, you will generate an extra volume for each function you select. So as the algorithm is a linear regression, these functions give the option for adding in nonlinear variations just to allow an extra degree of freedom to the algorithm. Next is the seismic operator radius. So this dictates how many vertically neighbouring seismic samples are considered above and below the well log sample position. The target, you need to define a number of target volumes, and then also the number of best sets iterations, which is key to the stepwise linear regression. So to start with, it will find the single best attribute or variation that approximates the well log. Then it will look for the best pair, but this must include the best single attribute. Next, the best set of 3 attributes or volumes will be found, but that must include the best pair, and so on until you reach the number of best sets iterations. You can choose to choose a validation well or a percentage of well data for validation. These won't be used in the regression. You can then choose to save your settings into this table here, which allows you to play around with various combinations of volumes and functions and to record your work. So for each job that's been executed, I can get to the attribute ranking result. So this gives me, in this case, shows me the best 3 functions or variations were the inverse of the amplitude, the inverse of the phase, and the inverse of the quad R. The square root of the quad R. And then for each of these results, I can see the coefficients for the attribute and function, and finally the error statistics. So I then have an option to create my regression volume from this panel. So if we go and have a look at one of these output cubes, so this is a porosity volume created from one of these attribute ranking results. So we can go and QC against some of the porosity logs. So the point of the algorithm is not an exhaustive search. It's not going to try all combinations as if it takes too long. So it's possible it may miss some combinations. It's just going to take forward the best set from each iteration. Also, it's important to remember you're never going to get a perfect result, as it's just a linear system approximating real values. So next I'd like to jump to the reservoir engineering toolbox and the new tartan gridding process, which is positioned as a process under corner point gridding. So this tool has been developed in association with Noble Energy in the US. So the new tartan gridding process offers the opportunity to increase the resolution and accuracy of numerical solutions to the flow equations around complex well geometries and in specific areas of interest. The gradual change you introduce in the grid cell size reduces the extent of numerical artifacts in the simulation results. Tartan gridding can also be used as an alternative in places where you don't want to use a local grid refinement. So Petrel also has native tartan gridding. However, this new interface provides greater flexibility in the gridding, smoother transition of cell growth, more features and more user interaction. So I'll just run through a quick demo. So the first thing I need to do is just to define my grid boundary with a polygon. Okay, so once we have that, we can start to add in kind of control lines. So just toggle to add in the I direction and also in the J direction. So all of this is kind of interactively updatable as well, which is quite nice. So for each kind of row or column we've created in the grid there, we have a new entry in this I direction table. So this allows us to play around with the method of cell growth between the control lines, so we can increase towards the center, increase to the east or decrease to the east. We can also play around with the number of cells and also control the growth of percentage cell growth. We can do the same in the J direction, again just assigning a method for cell growth. Again, we can play around with the cell dimensions and also again play around with the cell growth. So this is all still kind of dynamically updatable. We can continue to add in control lines and continue to add into this table. So we also have a few other tools available. For example, if you wanted to create a grid defined by a point set. So if I provide a point set here, so for example wellhead locations or known locations in a grid, I just click to run. It creates a quick grid based on all of the cell points. We can then come back to these I direction and J direction tables and start to configure the grid as we need to. So the output from this process is a new grid skeleton. So you then have to follow the standard Petrel workflow to generate horizons, zones and layerings, etc. So I have a quick example to show you. They're not particularly pretty or accurate, but just to show you the output. Okay, so just two grids coloured by I and J increments. So that was just a quick run through of the new tartan gridding process designed for the reservoir engineer to have extra control over grid resolution and generate improved flow descriptions through the new easy to use gridding process. So next I'd like to show you the interactive well picker. So this actually sits in the reservoir engineering toolbox. So creating wells in Petrel can be a little tedious perhaps. So creating XY wellheader information, Kelly bushings, total depths, etc. for each well. So we've managed to reduce this to the click of a button. So I'm just going to add in some 700 meter wells against this surface. So I click on my well picker icon, which is this one. I can then just start to click on the surface and add in 700 meter wells. We can also run this as inclined wells as well. So again, just start to quickly add in arrays of wells. We also have control over the number of wells, the inclination, and the range, azimuth range. So again, we're quickly building up nice well arrays. It's also a nice one to show you at this point that all of the Blueback tools are workflow enabled. So if I just scroll down, here's all the tools from the toolbox. So I just run a quick example with this create well at position, which is the interactive well picker we were just looking at. So there you go, I've just added in a quick regular grid of 25 equally spaced wells. Okay, so the final tool from the version 11 release is from the project management toolbox is the new MPD well loader. So this loads exploration or development wells headers directly from the Norwegian Petroleum Directorate fact pages on factpages.mpd.no. So wells are loaded within a user-defined polygon. The lat longs from the MPD are converted to the Petrel project CRS. So I'll just show you some wells that I've loaded through this method. So all the wells are loaded as vertical trajectories, as deviation surveys are not available on the MPD site. All the well symbols are converted to Petrel well symbols, and well attributes are added as user-defined attributes in the Petrel well manager. So you get quite a lot of information with all of these wells that are loaded. So for example, we have operators and target information, formation at TD, drilling days, rigs, etc., etc. Okay, so that concludes the demo of the Toolbox version 11 release. So I'm just going to run you through a quick preview of the Seismic Reservoir Characterization Toolbox, which was released a few weeks ago. But as I say, there's a full webinar planned on this in January 2012. So the seismic net pay workflow is a simple and robust method for net pay estimation. The workflow has been used by BP with great success in the North Sea and other regions, and it was first published in early 2000 and has since become a proven technology. So the Blueback Reservoir software development team have brought together all of the tools required for net pay estimation into a single suite of tools contained within the SRC toolbox. In addition to native Petrel functionality, the inclusion of rock physics, inversion and picked zero crossings will allow the user to run a complete seismic net pay workflow within the Petrel interface. So all of these tools also are workflow enabled, which allows easy repetition of the process. The input parameters can be adjusted to quickly see the consequences. For example, how does the selected chi angle affect resulting net pay? It was also allow the process to be run in loops, so we'll be able to plot, for example, total net pay against a range of EEI angles. So starting with the seismic intercept and gradient, this is kind of key to the SRC workflow. The tool calculates intercept I and gradient G volumes from angle stack seismic data. The next tool is the EEI angle analysis. So this takes VP, VS and row data, log data, and calculates and plots AI, GI on a log plot. By adding a projection line and fitting to the data the optimum chi angle to discriminate between the desired fasces can be found. The tool will also plot AI and GI data onto a cross plot and project onto a histogram, which helps to choose the chi angle. So the output surface and EEI reflectivity seismic attributes will be updated interactively in a 3D window as the chi angle is updated using the slider. This has been designed as an easy to use tool and will give the user a good feel for results. Next is the coloured inversion operator design. So this is the first time coloured inversion is available within Petrel inside the new SRC toolbox. The tool allows the user to design an operator wavelet for coloured inversion. The tool is effectively split into 3 sections, so creating an average well spectrum, an average seismic spectrum, and then QCing of the final operator. So the coloured inversion is the process of colour inverting the EEI reflectivity volume. We then have the surface snapping. So this allows the user to snap top and base reservoir surfaces to the nearest seismic feature. This is currently done in Petrel using the auto tracking, but a new, simpler way of snapping surface and horizons is introduced in this toolbox. Next is the seismic net pay. So we create a tuning curve. So top and base reservoir 0 crossings are picked automatically. You can measure apparent thickness and average band limited impedance. We then need to run the calibration from the tuning wedge, calculate a scalar to convert apparent thickness to net pay, calibrate seismic data using the color inverted seismic operator, and also calibrate against well data using known net pay values or well tops and selected well logs. Finally, the output. So this produces various maps, including the all-important net pay. So, hang on, bear with me. So as I mentioned, all of these tools in the SRC toolbox are workflow enabled. So this allows easy repetition of the process. The input parameters can be adjusted to quickly see the consequences. So as I said, how does selected chi angle affect resulting net pay? You can play around with the coloured inversion, cutoffs and tapers, and you can also, so it also allows the process to be run in loops. So one will, for example, be able to plot total net pay against a range of EEI angles. So that's it, demo-wise. So of course this was only a small selection of the 100 or so tools we have available in the toolboxes at the moment. Obviously it'd be difficult to fit them all into half an hour. So if there's anything I've not covered but you would like to see, then please get in touch with us on sales@bluebackreservoir.com. So everything we've seen in the tool today is available on the Ocean Store. The individual toolbox licenses are just under $7,500. However, we offer bundles of licenses which are a very, very cost-effective way of getting more licenses to more users. So everything we've seen you can take on a 14-day evaluation period. And just to touch on the SRC toolbox as well, this is also now available on the Ocean Store and is also available as a free 14-day evaluation. And again, as I mentioned, there will be a full webinar on this toolbox in January. Okay, so I'll just have a look, see what questions have come in. Okay, I'm not seeing any questions, so I guess okay, so I guess we cover support, however, support for 2010 and 2011. We have a patch release coming out soon. We also have another quite large update for this toolbox, or the core toolbox, so geology, geophysics, project management and reservoir engineering coming out, which is scheduled for March next year. So I guess that's it. If there was if you have input any questions that we haven't got back to you, we'll get back to you via email. So thank you very much for your attendance. I hope you found some value in the presentation, and that's it. Thank you very much.